I've written on the board here what's called the binomial theorem. And the binomial theorem says that x plus y to the nth power, where n is a positive integer, is equal to n over 0, x to the n, y to the 0, n over 1, x to the n minus 1, y to the 1, n over 2, x to the n minus 2, y to the 2, so on and so forth, out to n over n, x to the 0, y to the nth, where n over r is equal to n factorial divided by the product of r factorial and n minus r, quantity factorial. So these are binomial coefficients right here, and most of the time we will get them simply by using what's called Pascal's triangle. What you want to notice is that the sum of the exponents in any term, okay, has to add up to this n right here. So if n is equal to 3, the sum of the exponents on any one term is going to be 3. If n is 4, the sum of the exponents will be 4. They start with n on the variable x and decrease by 1 each time as the exponent on y starts at 0 and increases by 1 each time. So this formula you can use to expand x plus y to the nth power for any integer value of n, positive integer value of n, which saves us from having to actually multiply these big things out. So what we want to do now is go to the board and practice using this formula, the binomial theorem. We have, for problem number 1, x plus 2 to the 4th power. Okay, so I want to expand x plus 2 to the 4th power. First of all, I'm just going to take care of the exponents on x and on 2. So I won't worry about the coefficients yet. There will be some number, x to the 4th times 2 to the 0, plus x to the 3rd times 2 to the 1, plus some number x to the 2nd times 2 to the 2nd, plus some number x to the 1st, 2 to the 3rd, plus some number x to the 0 times 2 to the 4th. So you can see that the exponent on x starts at 4 and decreases by 1 each time till I get down to 0. Likewise, the exponent on 2 starts at 0 and increases by 1 each time till it ends with 4. And the sum of the exponents on any one term is equal to this exponent 4. Now, the only thing I have left to do is to fill in these coefficients, and I'm going to do that by using what's called Pascal's triangle. Now, you can see Pascal's triangle in the book. It always starts with a 1. In each row, the first number is a 1. This third row is 1, 2, 1. The next row is 1, and then I add these two numbers to get this number, add these two numbers to get this number, and end with a 1. Start with a 1, add these two to get this number, add these two to get this one, add these two to get this one, and end with a 1. Now, this row has 1, 2, 3, 4, 5 numbers in it, and that's what I need here, 1, 2, 3, 4, 5 coefficients. So this row of Pascal's triangle always matches the coefficients in the expansion of x plus y or a plus b or any binomial to the 4th power. So I can always tell which row of Pascal's triangle I need by looking at the second element or the second number in the row. It matches the exponent on the expansion I'm looking at. So these are the coefficients in this expansion. I'm just going to put them in now. 1, 4, 6, 4, 1. And that's all it takes to expand x plus 2 to the 4th power. Now let's actually just write it out. 2 to the 0 is 1 times x to the 4th times 1. It's x to the 4th. 2 to the 1 is 2 times 4 is 8. X to the 3rd. 2 to the 2nd is 4 times 6 is 24. X to the 2nd. 2 to the 3rd is 8 times 4 is 32. X to the 1st. Plus x to the 0 is 1. 2 to the 4th power is 16. And so I end up with this result, which is the expansion of x plus 2 to the 4th power. And I did it without actually having to multiply it out. I'm just using this binomial expansion right here. I take care of the exponents on the variables first, then I fill in the coefficients using Pascal's triangle. Finally, I simplify, and this is the answer. Let's go to the board now and work another problem. Number 2, I have 4x minus 3y, that quantity, to the 3rd power. So I'm going to expand this. This is going to be some number times 4x to the 3rd power times negative 3y to the 0. So I'm not going to write that because I know that will be 1. Plus some other number, 4x to the 2nd power, negative 3y to the 1st power. Plus the coefficient, 4x to the 1st power, negative 3y to the 2nd power, plus the coefficient 4x to the 0 power, which is 1. I won't write that, so negative 3y to the third power. Okay, now for my coefficients, I use Pascal's triangle, and I'll go down to this row that has a 3 in this position right here. So it's 1, 3, 3, 1 for the coefficients in Pascal's triangle. Now let's just simplify. 4 to the third power, 4 times 4 is 16, times 4 is 64, x to the third power. Plus, well now let's see, I'm going to have negative 3, 4 to the second, 4 times 4 is 16, 3 times 3 is 9, 9 times 16 comes out to be, let's see, 144, x to the second, y to the first, and then it's a negative sign because I have negative 3 to the first power, which is negative 3, so that changes that to a negative sign. Let's see, negative 3 squared is 9, times 4 is 36, times 3 is, I worked this out ahead of time, 108, x to the first, y to the second, plus negative 3 to the third power is negative 27, and then I have y to the third power. So you can see the exponents on x start at 3. It goes x to the third, second, first, x to the 0. The exponents on y start with y to the 0, y to the 1, y to the 2, y to the 3, or the sum of the exponents on any one term have to add up to this 3. Where do these coefficients come from right here? They come from Pascal's triangle. So Pascal's triangle works when you're taking things to the third, fourth, fifth, sixth, seventh power, things like that. Then you'll get exponents that are easy to find from Pascal's triangle. When you get to a little higher exponent, you actually have to go back and use the formula. In any case, let's go to the board and work another problem. Problem number 3, x minus y to the 10th power. Okay, when I expand this, this is what I'm going to get. I'm going to have to use my binomial coefficients, 10 over 0, x to the 10th, y to the 0, plus 10 over 1, x to the 9th, y to the 1, plus 10 over 2, x to the 8th, y to the 2nd, plus 10 over 3, x to the 7th, y to the 3rd. Now, from Pascal's triangle, 10 over 0, that's always going to be, or any n over 0 is always going to be the number 1. X to the 10th, y to the 0 is 1. Plus 10 over 1 is always going to be just 10. X to the 9th, y to the 1st. Now to calculate 10 over 2, the calculation looks like this. 10 factorial over 2 factorial times 8 factorial, but what really happens is this. It's 10 times 9 over 2 times 1, x to the 8th, y squared. Now when I show you the next one, you'll see the pattern. 10 over 3 is this. 10 times 9 times 8 divided by 3 times 2 times 1, x to the 7th, y to the 3rd. So whatever this second exponent is right here, that's the number below in this binomial coefficient expression. So when it's 10 over 2, it means this. Take 10 and multiply times each integer down below it until you've got two products, two factors that is, 10 times 9, then divide by 2 times 1. When this is a 3, I have to go 10 times 9 times 8. I get the first 3 factors, and I divide by 3 times 2 times 1. That's the result with these binomial coefficients. Now I want to continue to simplify. This is x to the 10th plus 10 x to the 9th y plus 10 times 9. That 2 divides into 10 5 times. 5 times 9 is 45. X to the 8th y squared. Plus 3 divides into 9 3 times. 2 divides into 8 4 times. 3 times 4 is 12 times 10 is 120. X to the 7th y to the 3rd. So here are the first 4 terms in the expansion of x minus y to the 10th power, and whoops, it's x minus y to the 10th power, so I need to change this sign to a minus sign or subtraction sign, and this sign also, because it's negative y in each case to these powers. So when I have an odd power, that will turn it to subtraction like this. So you can calculate these binomial coefficients using the long form if you want, or using this little shortcut form right here. Or you could extend Pascal's triangle down 10 rows and just use the first 4 numbers in Pascal's triangle. You'll see they will be 1, 10, 45, 120. Let's go now and look at the next problem. So let's see, this time I just want to write the first two terms. And you know in Pascal's triangle, the first term in every row is 1. The second term always matches the exponent. So when I expand this, I'm going to get 1 x to the 100th times 2 to the 0. The next term is going to be 100 x to the 99, 2 to the 1. Now does that stay on the board there? Okay, yeah. X to the 99, 2 to the 1. So this should be an easy one to simplify. 2 to the 0 is 1, so I just get x to the 100 plus 2 to the 1 is 2 times 100 is 200, x to the 99th power. So there is the first two terms, just the first two terms in the expansion of x plus 2 to the 100th. By being familiar with Pascal's triangle, I know the first number in each row is 1. The second number in each row matches this exponent that we use that row of coefficients for, and so I'll just have 1 and then 100 for my first two coefficients. Then I know it's going to be x to the 100th, 2 to the 0, x to the 99th, 2 to the 1. The exponents always add up to this number right here. So that's a little easier if I just want the first two terms in the expansion of x plus 2 to the 100. In any case, those are some examples that involve the binomial theorem that allow us to expand binomials raised to any positive integer x